So today we continue on with our discussion of postulates. I'll give you quite a few today. They'll all be algebraic in nature. Um, they're not the only algebraic ones that exist, but they're the ones that we'll use most commonly. And what I should emphasize here is this, is that, as I said last time, postulates are not just these like inert facts that just sit there and, I don't know, you memorize them and then that's about it. Rather, they are, as I said last time, engines of inference. They get us from one statement to another statement. They, as it were, prove that if a given statement is true, then this other statement must be true as well. So let me take a little bit of time to go through them. Some will be quite familiar to you. I think all of them will be actually. But there are some subtleties involved, so we'll take our time. So first of all, reflexivity. It says this: for every quantity x, every number x, if you like, x is equal to x. In plain English, every quantity is equal to itself. So for instance, the length of segment AB is equal to the length of segment AB. That's the first of our examples. And then the second is the measure of angle ABC is equal to the measure of angle ABC. Now, of course, a very good question is, well, yes, this does seem true, but why do we ever need to say this? It will happen in the next chapter, well, not the next, but chapter 4, actually, about congruence, where we prove triangles are congruent to one another. I'll tell you what that means later. Actually, statements of this sort will be very important. It will be very important to say that an angle is equal to itself, or a side is equal to itself. So there it is, reflexivity. Now, transitivity of equality, which is one of the most important inference rules that we will have in the entire class. So many of our proofs will end with an instance of transitivity. And what it says is this. Let us say that we have quantities x, y, and z, where x is equal to y and y is equal to z. Then it follows that x must equal to z. This is the way that Euclid put it. Things equal to the same thing are equal to one another. And let us make sure that you understand why that works. So let's see. In x equals y and y equals z, then x equals z. Do we have two things equal to the same thing? Well, yes, we do. We have one thing x and a second thing z, both equal to y. And then what we say is that those two things, since equal to the same thing, are equal to one another. That is, x is equal to z. So here's an example. Let us say that the length of segment AB is equal to the length of segment EF, and the length of segment EF is equal to the length of segment IJ. Then it follows that AB is equal to IJ. So here perhaps is a third way to put it. I had one quantity equal to a second, one equal to a second, and then I had that second equal to a third quantity. And then what I concluded that was that the first is equal to the third. That's just transitivity again. And it should seem just obviously true to you. All right, substitution, an extraordinarily powerful rule. It will be used in many of the proofs that we do, especially those that involve any kind of algebraic work at all. This does often happen. So let us say that we know that x is equal to y. Okay, whatever x and y happen to be. Okay, they can be like segment names or angle names or whatever they are. So if we know that x is equal to y, then in any expression or equation or sentence or absolutely anything at all, wherever we find x, we can replace that with y. Substitution is really a kind of replacement rule. When x is equal to y, then we can replace either x or y with the other wherever we choose. So let us say, for instance, that we know that x is equal to y and x is greater than z. It follows, of course, that y is greater than z. And how did that happen? Well, what we did is we took that inequality x greater than z, and we took that x and we replaced it with a y. And the reason that we were able to replace it with a y is that y is greater than, is that x is equal to y. So it follows that y is greater than z. So how about the next one? Let's say that if x is equal to 180 degrees over 2, then it follows, of course, that x is equal to 90 degrees. Now, how did we get from the first statement to the second statement? Well, the difference between the first statement and the second statement is the right-hand side of the equation. The left-hand side in both is x equals. So what happened is that the 180 over 2 was replaced by what it is equal to, that is 90 degrees. And whenever we replace something by what it is equal to, that is always substitution. Now, there is a certain relationship between what I call transitivity and what I call substitution. All transitivity is an instance of substitution. Like transitivity is a specific variety of substitution. So let's make sure we understand why that's the case. So let's say that we're given that AB is equal to CD and that CD is equal to EF. That is one thing AB is equal to, oops, I'm going to get rid of that. So let us say that one thing, AB, is equal to a second thing, CD, and that second thing, CD, is equal to a third thing, EF. Then it follows, of course, that the first thing, AB, is equal to the third thing, EF. And that's obviously an instance of transitivity, but you can also understand that this works by substitution as well. So here's what we can do. Look at that equation that CD is equal to EF. Okay, we can replace the CD, or excuse me, look at the equation AB is equal to CD. Okay, that's one of the given equations. And then we know that CD is equal to EF, so that CD is equal to EF. What that means is that the CD can be replaced by the EF. And then when we do that, we end up with AB is equal to EF, okay, the same conclusion that we had before. So we can understand this inference by either, we can describe it as either an instance of transitivity or as an instance of substitution, okay? And I know that this can confuse a little bit, so let's talk about this a little bit more. This is something that will be stressed multiple times throughout the class. Um, so we have said that all transitivity, every instance of transitivity, can be understood as an instance also of substitution, but it does not go the other way around. Okay, so let us say, for instance, that we have that AB is greater than CD. So there it is, and CD is equal to EF. It follows by substitution that AB is greater than EF, and notice what we just did to get there, right? So we took that inequality and we replaced the CD by what it is equal to, namely EF, So there we go. To get that AB is greater than EF. So this is definitely substitution. Okay, we replace CD by what it is equal to, namely EF, but it is not transitivity. And the reason that it is not transitivity is that transitivity requires two equations. Transitivity is that if one quantity is equal to a second and that second is equal to a third, then the first is equal to the third. So transitivity is all equality all throughout. But substitution works even in cases where we don't have all equations all throughout. Substitution does require one equation. It does require that some quantity equal a second quantity. But the other statement that it works with doesn't have to be an equation. Now, I know this is all a bit subtle, and we'll definitely come back to it and discuss it in detail, and it comes up on the assignment as well. All right, so we have properties here. We have postulates, I should say, called addition, subtraction, multiplication, and division. So let us say that we know that quantity x is equal to quantity y, and that quantity a is equal to quantity b. Then it follows that x plus a is equal to y plus b, x minus a is equal to y minus b, a times x is equal to b times y, and x over a is equal to y over b, where of course a is not equal to 0, which would mean that b is not equal to 0 as well, because a and b are equal. And that, of course, because we cannot divide by 0. Now, I know this is a bit complex to say, but the idea behind it is really extraordinarily simple. Number one says simply that if you add equals to equals, you get equals. X was equal to y and a was equal to b, so x plus a and y plus b are equals added to equals. And when equals are added to equals, you get equals, and equals subtracted from equals are equals, and so on. So these are very important. Law of trichotomy. This will be key for us in many of the proofs that we give. And it says this: let us say that we have two quantities x and y. One and only one of three possibilities obtains. Either x is equal to y, x is less than y, or x is greater than y. It must be one of the three. And what that means, of course, is that if we are able to rule out two of the three, then the one that remains must be true. So for instance, if we know that the measure of angle ABC is not less than 90, and we know that the measure of ABC is not greater than 90, it will follow that the measure of angle ABC is equal to 90 degrees. And we will definitely give proofs later on where that's how we reach our conclusion. We rule out two of the three possibilities, and then we conclude by the law of trichotomy that the third possibility must be the one that is true. Now, there are, of course, other algebraic postulates, ones that you've seen in your algebra class. Distribution comes to mind, association as well. If the need arises, we'll simply give the algebraic name when we make one of those types of moves, like the distribution move, but they don't happen too often, so I decided not to list them out. All right, so let us look at examples of what these postulates do for us. What they do for us is what the geometrical postulates do as well. That is, they get us from one statement to another. That is, they allow us to infer a second statement from a first statement. So here are examples and also non-examples of inferences. And so let us pick out the examples and explain why they are examples. And the non-examples, we'll pick those out too and explain why they're non-examples. So here's the first. If AB is equal to CD, then AB over 2 is equal to CD over 2. So does that second statement, the one after the then, previously we used thus, but then works in the same way, does the second word, does the statement after the word then follow from the statement before the then? That is, if AB is equal to CD, does it follow that AB over 2 is equal to CD over 2? And the answer is absolutely. Of course it follows, right? Now the question then is, what got us from the first statement, AB equals CD, to the second statement, AB over 2 is equal to CD over 2? And notice what happened as we went from the first to the second. We divided both sides by 2. And that's what division allows us to do. So how about this? If the measure of ABC is 90 degrees over 2, does it follow that the measure of angle ABC is 45 degrees? And the answer is, of course, right? Of course it does. And perhaps you will be tempted to say that this is also division, but it absolutely is not. Because what division does is it takes an equation and then divides both sides by the same quantity. That did not happen in this case. Look at the left-hand side of each of the two equations, the one on the left and the one on the right. They're both simply the measure of angle ABC. It did not get divided by anything, so this is not division. Instead, what happened is this, is that the 90 degrees over 2 was replaced by what it is equal to. That's the logic of this. And of course, it's equal to 45 degrees, so we have 45 degrees on the second statement. So what then is that rule that allows us to replace some expression by what it is equal to? That, of course, is substitution. So yeah, it follows by substitution. So how about this? AB isn't larger than CD, then AB is less than CD. Well, obviously that just doesn't follow. That doesn't have to be true. It could also be true that AB is equal to CD. So this looks like a illegitimate use of the law of trichotomy. To use the law of trichotomy, we have to eliminate both possibilities, and then we conclude that the third must be the case. When we said that AB isn't larger than CD, we only eliminated one of three possibilities. So doesn't follow. So how about this one? Let's say that AB is equal to MN and that FG is equal to MN. Does it follow that AB is equal to FG? Well, yeah, absolutely. And this is very much like Euclid's formulation of transitivity. I have two things, namely AB and FG, both equal to the same third thing, namely Fn, and it follows then that those two things, AB and FG, are equal to one another. So yeah, this follows by transitivity. But recall the point that we made about transitivity. Everything that is transitivity can also be called substitution, though the reverse of that is not true. Just to remind you, there are instances of substitution that are not transitivity. And that is it for algebraic postulates. What we'll do in the next section is we'll start to put together chains of inferences, okay, where we don't simply have two statements, but we have many, many statements. And then what we'll find is that every statement after the first will follow from some statements that come before. And that is then just simply sort of chained examples of what we've done in these first two sections. And I'll go ahead and tell you that when you put chained examples together, that is many inferences together in this way, you'll have something that looks very much like a proof.